Hi everyone, my name is Cameron Lowe and I'm going to be talking about the element method for superalignment design. If you've just watched Steve Kostakis from EXDS's presentation, you'll be familiar with the IP method. And the element method, on the other hand, is a more advanced but complex design method. But you do get payoff for going through the added complexity, and that payoff is flexibility, speed, and accuracy of your designs. And it'll mean you embrace change rather than dread it. So I'll be starting off talking about the different element parts which we get access to with the element method. Then I'll discuss how these element parts fit together to define our horizontal and vertical geometry. I'll then jump into 12D and create a superalignment using these element parts. Then in the next talk in this little series, Rod Burns from EXDS will discuss further capabilities of the element method and how we can improve and automate our designs even further. So we know the IP method. If you've just watched Steve's presentation, then you'll know that in its most basic form, we pick points for the straight lengths of the road, whether that's for the horizontal or vertical geometry, and then we apply a radius or length to create the curved lengths of road. We do have some useful tools for placing these IPs, like using SnapsCAD and the various insert and intersect and change tools on the superalignment edit toolbar. But for the IP method, this is pretty much the basis for how geometry is produced. But when we need to make changes to our design using the IP method, we tend to have to go through a lot of manual changes and calculations, particularly of new IP points, which just takes more time than it has to. In this case, if we want to shift the straight length of road, we have to calculate the two new IP positions to produce this shift. But wouldn't it be easier to just offset that length and let 12D work out the details for you? This is what the element method enables. We can define our geometry not with IPs, but with geometrical features like points, directions, radiuses, and lengths, which all communicate with one another along the superalignment. So we can make changes much more efficiently with less manual work and with less likelihood of errors. So now I'll talk about the element parts which enable this to happen. The first element part in our arsenal is the fixed line. This element part is used to define straight lengths of road, whether that's horizontal or vertical. In this PowerPoint, I'll just talk about horizontal geometry, so I can be clear, but the principle is the same for vertical geometry. So to define a straight length of road, we need two pieces of information. Either two X and Y locations, or one X and Y location and a direction. And then importantly, when we've created this fixed line, we can be really quick when making any changes to the inputs. So, as I mentioned before, we can simply add an offset, or change the direction of the element part, or move the point or points themselves to define the new geometry for the straight length of road. So we have a lot more options when it comes to change. And that's fixed lines. Now when you're starting out with the element method, you'll primarily be using fixed lines for straight lengths of roads and free arcs or free parabolas for vertical design as your curved lengths. So typically we'd have two fixed lines which intersect at a certain point, which we let 12D calculate. This would be our IP point, but it's not an important point for us now. And we need to specify either the radius of the curve or a point to pass through, and 12D will work out the radius, or an arc length, and again 12D will work out the radius for us. So for a lot of common geometry, you'll find that the fixed line and the free arc element parts are enough to get you through. There are some less commonly used element parts which have their own place and their own purpose, so I'll go through these fairly quickly. So the first of those is a fixed arc. These fixed arcs require three pieces of information to work and to define the geometry of a curve. But unlike a free arc that we just looked at, these fixed arcs can define geometry on their own. And they don't require other element parts on either end to solve and to therefore define geometry. So for these, we need 3 points, as we have there on the left, or we need a point, a radius, and a direction, as we have on the right. There are a few other options which I won't go into. Then we come to a floating arc. For this element part, we rely on having another element part on one side of it to run off. And we need 2 data points. So either 2 points, or a point and a radius, or a point and direction to define the geometry around a curve. Then we have a floating line. So a similar concept to the floating arc in that we need an element part on one end to run off. But for a line, we only need one input. So that's either the direction or selecting a point to pass through, and then the line will be created tangential to the arc that it's connected to. Or the third choice is just a length, which will be applied tangential to the end of the arc for a certain length. And then lastly, we have free lines. And free lines require no input. So what they do is use the element parts on either end of it and automatically solve the geometry between those 2 element parts. In this case here, the free line will be solved so that it's tangential to the curves on either end of the line. And the extension of the arcs will be trimmed out, which you can see there with the dotted parts of the line. So those dotted lines won't form part of the final geometry. And this is a good example of the communication between certain element parts and the element parts next to them. In this case, if we were to change the radius of one of these fixed arcs, that free line is now tangential in a completely different way to both of the arcs on either end. So both the line will change and the 2 arcs will change as well. So in this situation, not only does a change affect the element part next to it, but potentially an element part 2 away as well. So when I learned the element method, the way it was taught to me and how I continue to think about how I use these element parts is with an analogy which uses tables. So in this representation, a fixed element part is like a table that has 2 legs. So what that means is it can stand up and therefore it can define geometry on its own. A floating element part is like a table that only has 1 leg. So it needs a leg on its other side to stand up and therefore define geometry. And then a free element part is like a tabletop. So it requires legs from element parts on either side of it to be able to stand and to be able to define geometry. So I'm not going to overdo this analogy too much, but how this is going to help us is just to initially help determine which element parts we'll use when we're creating our superalignment. So before we create the geometry, we can plan out which element parts we're going to use and where. So let's jump into 12D. Okay, so in 12D now, this road here, which ends in the cul-de-sac, we're going to be designing the superalignment reference string for using the element method. So the way that you create the superalignment is the same whether you're using the IP method or the element method. We select strings, superalignments, create superalignment. Now I've already set up the general node here to have all the naming that I require. And the changes I'm going to make based on the defaults are in the labels tab. I'll change the labels to design LHS, the major interval of 100 and minor interval of 20. And then in the sync node, I'm going to tick on vertical sync. Okay, and then select create. I'll come back to that vertical sync and explain exactly what that is in just a minute. But that creates the superalignment edit toolbar for us here. Now, when we're designing using the IP method, we primarily use these first 3 icons. But now we're going to be using this icon here, which is the part editor. So I'll select that one. And this is where we place the horizontal and vertical parts. Now to place a part, I'll just select the horizontal and then select insert. So we're going to design our horizontal geometry first, and then profile that superalignment, and then design the vertical geometry in the section view. So select insert. And it's always a good idea, as I said in the PowerPoint, to plan out which parts we're going to use and where along the superalignment. So this first straight length of road we're going to design as a fixed line. Then our horizontal curve is going to be a free arc. Then we're going to use another fixed line for the next straight length of road. And that will take us to the center of the cul-de-sac. And then we'll add on a floating line to add on some additional length of the super alignment. Okay, so the first part is going to be a fixed line. I'll select the filter icon, expand line fixed, and we have two options, 2 points or point and direction. I'm going to select point and direction. And then, as we'd expect, we need to select a point and a direction. So the point will be the start point of the road. To select that, I'll select the pick icon, and then using our SnapsCAD, right click, walk right over SnapsCAD, walk right over intersection, and then select two offset segments. So I'll pick that one there. The first offset segment will be the intersecting super alignment. Pick and accept. Offset of 0, and enter. And then for the second offset segment, well, we need the super alignment to be at the center of this road reserve. And I know that this road reserve is 16 meters wide. So I'm going to pick with direction, pick and hold, drag, release, and accept, and input half of that road reserve width, which is 8 meters. And enter. And that will place the point. So now when we select in either the X or the Y coordinate fields, we get a green circle there, which is centered around that point. So that looks all right. Then for the direction, I'm going to use the measure icon, measure point to point, and select bearing. And the bearing of the first length of the road is going to be the same bearing as the road reserve. So I'll pick my 2 points on the road reserve, pick and accept, and pick and accept. And that will enter the bearing into that direction field. Now for the relative start and relative end, this is what's just going to define the initial length of this part. So relative start, I'll put as 0 because we're at the start of the super alignment, and relative end I'll put in as 50. And then select set. And because this is a fixed part, it can define geometry on its own. So that's why you can see there that the geometry of the road has been created. So we can move on to our next parts now. So I'm not going to create the free arc just yet. I'm going to create the second fixed line first. So I'll insert another part and select the filter icon, expand line fixed, and this time we're going to use the option 2 points. So I'll pick that one, and as you'd expect, we need to select 2 points to define the horizontal geometry for this straight length of road. Now the start point, we just need to place somewhere at the center of the road reserve. Now if I just toggle on my vertices, you'll see that we do have a straight length of road at the top here, or straight length of road reserve, and we do have a straight length of road reserve on the southern boundary here. So we are able to place a midpoint between these two segments to find somewhere at the center of the road reserve. So to do that, I'll select the pick icon, and then again using SnapsCAD, point, midpoint, and then pick and accept a point at the center or somewhere on that northern segment, and then pick and accept somewhere on the southern segment. And then we know that this start point is somewhere on, well, it is on the center of the road reserve, and that's all we really care about. Okay, then for the end point, we want to select the center of the cul-de-sac bulb. So to do that, I'll select the pick icon again, and this time we're going to be stacking our SnapsCAD commands because we want the center of the circle defined by this road reserve here. So right click, walk right over SnapsCAD, walk right over point, and select center. And then again, right click, walk right over SnapsCAD, walk right over circle, and we'll select 3 points. So 3 points, and then I'll define the circle with the 3 points. So I'll just pick and accept, and then pick and accept. And when I select in the X or Y coordinate fields, you'll see we get the center of the cul-de-sac there. All right, now importantly, we need to pay attention to what happens to this first part when we select set on this part. So currently it's 50 meters long. If we select set now, you'll see that that first part extends to meet the extension of this second part. So we've essentially 12D has calculated this IP point for us, but we haven't defined that point. Instead, we've used points and directions to define our geometry. Okay, so now we've got those first two parts, we can add in our horizontal curve. So I'll go back to part number 1 and select Insert. And then under the Type field, I'm going to be using a free arc to define the horizontal curve. And that's going to be defined using a radius, so I'll pick radius. And all we need to define is the radius of the curve. So I'll just press F2 and inquire on the road reserve boundary on the inside of this curve. And you can see that last entry in the information panel there is the radius of -16. And with the element method, it is important that we get the sign of our radius correct. So this is a curve to the right, which means we need to be defining a positive radius. If we accidentally define a negative radius, I'll show you what happens. So we've got that 16 meter radius plus half of the road reserve is +8, which is 24. Now if I put in -24 instead of +24 and select set, you'll see the 12D thinks that is a curve to the left, so it will place a left curve, which is clearly not right. And so I'll take that minus off and select set. And that looks much better. Positive radius is curved to the right. And you see that that will automatically trim out the free lines, the fixed lines on either side of that free arc. Okay, and just so that we use one of each of these types of elements, I'm going to add in a floating line at the end. So when we design these cul-de-sacs, the superalignment should extend to meet the curb return, which runs around the cul-de-sac, and that has a radius of 10 meters. So I'm going to add in a floating line, which will just add 10 meters of length to the end of this superalignment. So I'll pick part number 3, and then select Insert. Under the Type, I'll select Line Floating, and I'll select From End. So this will adopt the bearing of the previous element part. So I select From End, and we just need to define the length. So I'll select a length of 10 meters, and then select Set. And you'll see in the plan view there that we now have 10 meters of additional length added onto the superalignment there. All right, and that completes our horizontal geometry. So now we can start looking at our vertical geometry. And to do that, I'm just going to profile this superalignment that we set up in the section view. So I'll select Profile, and then pick and accept on the superalignment. And I'll move this over here now because we're looking at the vertical geometry. Now between Steve from EXDS's presentation and this presentation, I created an apply MTF function on the intersecting road, this RS2B01 road, so that we have some road links to match into. So I'll add those design strings onto the section view, and you can see those here. So we have a crowned road with a high point in the middle of the road and falling away down to our lip of curb. So for the first length of our vertical geometry, we need to match into both of these points to maintain that crossfall for any car that goes straight through the intersection. Okay, so for the vertical geometry, I'll insert a new part. And the principle is the same as the horizontal geometry. Straight lengths of road, we're going to use fixed lines. So I'll expand, well, select the filter icon, select fixed line. And because we want to pass through those 2 points, I'm going to select 2 points. Okay, then we define our 2 points using a chainage and a height as opposed to a X and Y coordinate as we did for our horizontal geometry. Okay, to pick the first position, which will be the crest of our road, I'll select the pick icon and then just pick directly from the section view that location. Okay, and then for the end point, again, I'll use the pick icon and pick the lip of curb and accept, and then select set. Okay, so our first straight length of vertical geometry passes through both of those points, and you can see that grade is -3%. So what that tells me, because the carriageway crossfall of the RS2B01 road is -3%, that tells me that these two roads are perfectly perpendicular at the moment. Right, we'll create the other fixed lines for our vertical geometry before we create the free parabolas. So I'll select to insert a new point, and then under type will be line fixed, and this time I'm going to select point and grade. So I'll pick that one. Now I'm just going to specify a manual chainage and height, which we want to pass through with our vertical geometry. So I'll pass through chainage 58 and height 32.5 and apply a grade of 8% to that. And then just to set up the reference geometry, the relative start can be -10 and relative end can be +10. Okay, and then select set. And there you'll see now the next straight length of our vertical geometry will be passing through chainage 58, height 32.5, and have a grade of +8%. Okay, I'll insert another part just to finish off our vertical geometry here. Insert, again, select line fixed, point and grade. This time the point will pass through the end of the tin, so I'll select the pick icon, pick off just to the right at the end and select accept. And the grade I'll set as -3%. The relative start I can make -10 and the relative end of 0, and then select set. Okay, and that will complete that, those fixed lines. So it will pass through the end of the tin with a grade of -3%, which you can see there. Okay, now for introducing the parabolas for our vertical design. Between part number 1 and number 2, I'll insert a new part and then select the filter icon and expand parabola free, and I'll define the parabola using a length, and the length I'll set is 40 meters, and then select set, and that vertical curve will be added into our geometry. And I'll just copy that part, select part number 3 and paste. That will untick use, but I'll just tick that back on, and you can see the length there is still 40, and select set, and that will create the second vertical curve there. Now if we need to make changes to this vertical geometry, this is where the element method really comes into its own. So let's say, for example, we want to lift up this central straight length of road here. I'll pick part number 3, and rather than working out the new IP position that will correspond to this straight length moving up, let's say 0.5 meters, I can just add a height here, so plus 0.5, that'll become 33, and I can just select set, and that straight length will move up. So now it's running through chainage 58, height 33. Similarly, well, I'll just change that back and set. And similarly, if we want to change this grade to 9% or 7%, we can just change the grade here. Again, we don't have to work out manually those new IP locations. So I'll just select 7% there and select set, and now that central grade will change to 7%. So a whole lot easier to change these parameters and how we run our grading. Okay, but I'll change that grade back to 8 and set, so really easy to change. Okay, something I did want to show you was if we make changes to the horizontal geometry, now that our vertical geometry is set up, what effect does that have on the vertical geometry? So these changes that I've been making for the vertical geometry, they can also be made in a similar way in the horizontal, for the horizontal geometry. But if I just select the fifth part, you'll see that currently the end of the superalignment is at chainage 112.169. And you'll recall we added on, we ticked on the vertical sync. So now what happens if I change the horizontal geometry? So just remember this 112.169. We can also make changes in the horizontal. So let's say, for example, the road reserve shifts over by 5 meters. We don't then have to calculate the new start IP location and the new IP location at the horizontal curve up here. We can just go into this offset field and type in -5 and select set. Okay, and you'll see that the horizontal geometry automatically updates. Now, when we make a change like this, we need to decide what happens to the vertical geometry. And that's what we decide by ticking on vertical sync. What that vertical sync ticked on does is it attempts to keep the vertical geometry in the same location relative to the change in chainage. So if I go back to my vertical now, expand vertical and look at this part number 5, you'll see the chainage has been changed or updated to 114.6959, which is now the end of the superalignment. So that additional length of the superalignment has been added to this chainage. So that ensures, in this situation, that that point still passes through the end of the tin. Now, if we didn't tick on that vertical sync, then this chainage would have stayed exactly the same as it was, that 112.1629 or whatever it was. So it wouldn't actually now match to the end of the tin superalignment. So that's just a small example of what that vertical sync does. Okay, but there's an additional change that we can make to the horizontal geometry. If I just go back and change the offset back to 0 and set. We can also change the bearing through this interface. You see we put the direction in here for the first horizontal length of the road. If I reduce that, say, by -10 degrees and then select set, you can see we can change that direction of the first length of the road. Now, when we do that, we come into a different problem where now in the vertical geometry, we are no longer passing through, well, we're still passing through the crown of the road, but we're no longer passing through the lip of the curb, which you can see there. Now we could go into our vertical part editor and go into part number 1 and update this end chainage and height. So we could re-pick this point and then pick the new lip of curb and accept and then set. And now it would pass through and we would get that resultant grade. But that's really a lot more work than we need. So what Rod Burns from EXDS, if you continue and watch his presentation, which will be coming up after this one, he will introduce to you string references and computators, which are an additional capability of the element method for superalignment design. And what those string references and computators allow is for you to directly reference other string data when you are creating your horizontal and vertical geometry. So that if a shift occurs, whether it's the horizontal geometry or the vertical geometry, your superalignment will automatically solve and it will take on the new location of the other strings running off of your road. So in this case, if we change the bearing of this first straight length of road, the vertical grade will automatically shift to pass through our crown and the lip of curb. So we don't need to go through that additional manual, those additional manual changes, because they just take time and they introduce potential risk into your project. So I would definitely encourage you to watch Rod's presentation on that, because it really superpowers the element method for your super alignment design. Now I'll just change that horizontal back, so I'll just add on that extra 10 meters and set. And I do need to change the vertical grade back because I did switch that. So now pass through new location and set. Okay, and I can finish that part at a time. So that completes this presentation into the element method. Yeah, and we've really discussed the building blocks for the element method with those fixed, floating, and free parts. So I would encourage you, when setting up your super alignments in 12D, to explore this element method, because it really is a faster and more efficient way of designing your super alignments. Yeah, and I would encourage you to watch Rod's presentation, where you can really take your super alignment design to the next level and start referencing your other string information when setting up your super alignments. So thank you very much, and if you have any questions, please feel free to get in touch. Thank you.